So the next talk will be by Dr. Olivier Bock from IPGP-IGN, assessing and improving the accuracy of GNSS tropospheric products for climate research.
Okay, thank you for the introduction. Yeah, okay, so I'm coming back to the tropospheric topic and the application for climate research. And so I want to acknowledge my co-authors, and mention that this is a contribution to the IAG Joint Working Group C8, which is on GNSS for climate. Okay, so for climate applications and many scientific applications, we are looking into very accurate and stable products. And in terms of precipitable water, here are a few reference numbers of the target in terms of mean error, which we would like to be smaller than 0.5 kilogram per square meter or 2%. Which translates into a constraint on ZTD of 3 millimeters. In terms of stability, when we are looking to trends, we would like to have better than 0.1 kilogram per square meter per decade uncertainty, or 0.6 millimeter per decade. And of course, we also need realistic uncertainty estimates, because many applications, especially trends and detection of extremes, we want to assess the statistical significance of these detections, and we need correct uncertainty estimates. So what is the current state of the art, and what are the limitations of current products? Unfortunately, most of the time, for most of the analysis centers, tropospheric parameters are treated as side products. There is no real quality control or quality assessment applied, which means that there are often big outliers in the time series, and this requires some post-processing, and I will come back to that topic. Regarding the accuracy, in terms of absolute accuracy, we are concerned with biases in PW and ZTD, which we observe are highly station dependent, but no clear relation with the equipment is yet established. So there are other factors we need to understand. And as I showed in my presentation on Monday, there are also inhomogeneities in the form of bias changes or jumps, and we explain only a fraction of these thanks to equipment changes, to documented equipment changes. And the last point is on the formula errors. We know they are not representing the true uncertainty if we compare PW or ZTD to other meteorological observations, which are traceable to international standards. Okay, so that's the status. So the objective of this work is to better understand the causes of the different errors, which we classify into outliers, biases, and inhomogeneities. We want to improve the accuracy and stability of these products, which means that we are looking for optimal processing and post-processing procedures. And we want to improve also the uncertainty estimators. So I'm going to show a few results from different data sets. And the main focus will be on IGS Repro 3 solutions from 4 analysis centers. So this is some work we presented already in the past. And what I want to highlight here for ZTD, okay, these 4 analysis centers use different software and different processing details. And some of them are very important for the tropospheric delay, actually. So there are different processing modes, especially PPP or zero difference, which is network processing. And then another important point is the cutoff angle. We know that changing the cutoff angle can change the mean value. So you can tune the bias if you want, changing the cutoff angle, but this is more revealing that there is some elevation-dependent error source somewhere. And most important is actually the mapping functions, because this is the partial derivative in the mathematical model we use to estimate ZTDs and gradients. And in this study, we see that the different mapping functions have been used. So this can be some of the reason why we can have some small differential biases. And the last point I want to highlight is the ZWD constraints. So this will be actually the possibility for the estimation to produce ZTD variations in time. And most of the analysis centers apply loose or no constraints, which means that ZTD can vary in a big way from one point to the next, except GFZ is using Tikhonov regularization, which is more or less a tight constraint on this parameter. Okay, so let me come to the results. And the first point I want to discuss is the outliers. So we see here in these diagrams, you have ZTD on the horizontal and the formal error on the vertical. ZTD is physically only possible between 1 and 3 meters. Outside this range, it is impossible value. And we see that the three centers which do not constrain the parameters have values which extend much beyond this physical limit. And this is the first point I want to highlight. So this is a big difference between constrained and unconstrained estimation. Here, the numbers, the red shades show the area where it's not possible physically, and the percentages are small, but of course we are using millions of observations of data, so this small percentage still represents values which have no physical meaning. Another point, in the lower two graphs, the dark shaded area shows values where the formal error is small. So if we use that as an indicator of the uncertainty, we would say, okay, the ZTD has uncertainties better than 1 centimeter, but actually we see that some points are really big outliers in the red shaded area. So this is a problem which mainly we see in the network solutions and almost not in the PPP solutions. In this one and in others which we tested. Okay, so the outliers are actually very dependent on the analysis center, so on the software and the processing procedure. And among that, the data editing procedure. And what is not clear here, but if we look into details, we see also that the results are station specific. Most of the outliers are coming from stations from a few stations which have problems over some periods, so when the observations are degraded. Yeah, and these results are confirmed from past studies with other data sets in PPP and network in double difference solutions. Okay, so moving to the second topic, which is the biases. So with the four solutions, 4 data sets, we can do cross comparisons. And so we have 6 combinations, 6 pairs of differences. And each of the plots here shows the median value, which is a robust estimator of the mean, for each of the 200 common stations for the 4 data sets. So we see that for the 6 comparisons, the median of the whisker plot, which is the orange line, is close to 0. So on average, the agreement between the data sets is very good, but we see there is some dispersion, which means that some stations have quite a large bias, up to 4 millimeters, plus or minus 4 millimeters, which is explained partly by the difference in the processing, but not only. I will come back to that in the next slide. If we want to have an assessment of the absolute accuracy, we need a reference. So an easy reference is often to use the reanalysis. So here, the plot on the right shows the comparisons with ERA 5. And what we observe is that now the medians are not coincide with 0. So there is a small bias around 2 millimeters, which possibly is coming from the GPS, because this is also confirmed with independent comparisons with radiosondes. We don't have an explanation for that yet. But you can see that some stations now have biases up to 20 millimeters, which means that there is some biases are common in the solutions. Okay, now if we compute the standard deviations, so the variability of the differences between the solutions, we see again that there is on average a good agreement around 2 millimeters, a bit higher for one of the data sets from GRG. But again, there are some outliers, meaning that for some stations, there is a very big standard deviation of the differences. And if we use a absolute reference for the absolute assessment, we again see that there are some cases where the standard deviation of difference is large. So actually, these large values are not due to noise. If of course, we should always inspect the time series to see what it looks like, but to inhomogeneities, and this is something which I showed on Monday when we compare the solutions from different analysis centers or from one analysis center to ERA5. We observed this kind of time series where there are some biases for some periods, and in these cases, they are linked to the use of wrong or uncalibrated radome and antenna combinations. So, yeah, this means that biases, mean differences, and standard deviations alone may not always be very representative. We should always check the homogeneity of the time series. So I already talked about this segmentation tool, which is very useful to detect the change points in the time series, and which helps us to identify these problematic periods when there are biases or jumps. And but a step further is after the segmentation, of course, we want to correct the time series for climate studies, especially if we want to estimate trends. And so we need to attribute the jumps if they are due to GNSS or to the reference, in our case, ERA5, because we detect the jumps in the different time series, okay? So this attribution step is very important. It may be due to the reanalysis, because reanalysis assimilates observations, mostly from satellites. Satellites have a limited lifetime, and when there are instrument changes, there may be some small jumps. There are some small jumps, okay? And the last point is then the correction once we are sure the jump is due to the GNSS. We can also correct the reanalysis in that case, of course. Okay, okay, this is the link. This tool is freely available on GitHub, and attribution uses a random forest, which we trained with NGL data on 40,000 cases. So it is quite robust, and this is just one example of a jump which is detected by the PML-seg, validated with the metadata, which is just a control, but it's not formally used in the procedure. And then the attribution, which is only based on the statistical method, which attributes this jump to GNSS. Yeah, and so we applied it. This is also a slide I showed on Monday, to different data sets. And this is just to provide more insight into these results from the different data sets. So here I show the segmentation results for the 4 IGS Repro3 solutions, and also NGL, which I didn't introduce, but I think NGL is well known. It's based on gypsy processing. So it's constrained. It's a Kalman filter, so it's strongly constrained. And what we see from the 4 graphs is that more or less the 5 data sets show very similar statistical results in terms of number of change points detected, percentage of validations, except, as I already mentioned on Monday, NGL has a lower rate of validations because of the naming of the stations, and they don't use site logs for all stations. And the offsets, magnitude of offsets can be, it's typically between 2 or 4 millimeters, but can be up to 30 millimeters, the example I showed before. And the noise estimation, if you compare the offset and the noise, so it gives an idea of the signal to noise ratio of the detection method. You see that we are much better than SNR of 1 with this method. Okay. There are small differences between the data sets. Again, this is due to the fact that they don't use exactly the same processing procedure. Okay, and now coming to my conclusions. So, okay, mainly I just have only a few seconds left. We established some recommendations in our working group on the use of metadata. I already mentioned on Monday, it's crucial to have validated metadata. For the data processing, there are a few recommendations. For this kind of applications, we conclude that PPP is more efficient because it doesn't have the problem of the small formal errors when we have a big outlier. And also it's faster to process and to update. We also would recommend to use NWB-based mapping functions compared to empirical. And for the question of the constraints, it has a strong impact on the outliers. It's not clear yet if we should constrain strongly or not, because if you constrain, you would not see problems in the observations. So constraining should always be done at the same time as efficient data editing. And for the post-processing thing, okay, I think I mentioned already these aspects. And so this work is ongoing in the joint working group, and we are still open to welcome new participants with other software and data sets, and looking into the development of more enhanced post-processing procedures. That's all for me. Thank you for your attention.